If you've ever flown on a plane, odds are you're very familiar with turbulence, and it left you rather shaken. But despite turbulence constantly showing up in our skies or in whirlpools in our bathwater, scientists don't have a mechanistic framework to describe how vortexes drive cascades of energy that lead to turbulence. So, to try and develop one, scientists at Harvard busted out a high-speed camera, some colorful dye, and I can't believe I get to say this, vortex cannons. Two of them fit in a 75-gallon aquarium, where they fired plumes of liquid through water. The cannons were pointed squarely at each other so that the vortexes could meet in head-on collisions. Thanks to a little fluorescent dye, the scientists could then watch how the two vortex rings interacted when they met. Watching the results looks like the most over-engineered lava lamp you could ever imagine, but I promise you there is science happening. To capture the interactions of the two vortexes clearly, the researchers used a high-speed camera. That let them see everything clearly and smoothly in slow motion, but only in 2 dimensions on the X and Y axes. To get a 3-dimensional view of the interactions, they synced the camera with a pulsing laser that scanned the Z-plane of the collision. That way, for each frame from the high-speed camera, there would also be a laser scan cutting through the place where the vortexes collided. With the high-speed 3D models of the collision recorded, they could observe in detail what exactly was going on. They noticed that the rings stretched outward when they hit each other, and that antisymmetric waves formed at the edge of their expansion. The edges of those waves developed filaments that grew perpendicularly towards the opposite vortex. Neighboring filaments counter-rotated and created smaller vortexes. When those vortexes interacted, they also formed filaments, repeating the cycle. The researchers observed 3 generations of an orderly cascading cycle before everything broke down into turbulence. They think this could point to a universal mechanism of how energy cascades down until it dissipates, regardless of scale. This work has applications beyond making cool posters to put in a blacklit room. Modeling turbulence can help us predict weather patterns, map the flow in the oceans, or understand how an airliner can fly with eddies trailing behind it. And having a model for turbulence could also be useful as average global temperatures rise, because severe turbulence is expected to double or even triple by 2050. Yeah. Climate change is going to make air travel even bumpier. But this research is just a step towards that broader understanding. At the scale that jolts airplanes and makes you cling to the poor sap in the middle seat, things are a lot more complex than this experiment. Still, for a brief time at the late stages of the lab-made vortex collision, the experiment seems to have created the same conditions as real-life turbulence. So, more research is needed. I just hope the scientists stop before they create supervillain-level vortex cannons. Does turbulence worry you, or are you a smooth customer when the going gets rough? Let us know in the comments. High-speed cameras can pull off some really neat tricks, like seeing around corners. Marin has more on that here. Make sure to subscribe to Seeker, and thanks for watching.